Hello and welcome to ARM Dev Summit. My name is Jacob Beningo and I am going to be your presenter for this session, getting started with multi-core microcontroller applications. Now, before we get started and talking about multi-core microcontrollers, I want to give you a little bit of a background about myself. As I mentioned, my name is Jacob Beningo. I'm the president of Beningo Embedded Group. I'm an independent consultant that focuses in on real-time embedded systems. Now, as you can guess, my core focus is on microcontroller-based systems. Now, I've been doing this for over 20 years professionally, got started in 8-bit microcontrollers, writing an assembly language, and of course, nowadays we're doing all kinds of cool stuff, Rust, Python, C++, still writing in C code, but for far more sophisticated systems than obviously I started out on. So I've also published a couple of books, and I develop a lot of content, do a lot of webinars, give a lot of talks, and write a lot, developing content to share best practices with engineers and entrepreneurs who are trying to start businesses and who are just trying to develop real-time embedded systems. So if you want to learn a little bit more about myself, you can always feel free to hop on my website at beningo.com. But the core focus of what we want to talk about here today isn't me, it's multi-core microcontrollers. Now, from that standpoint, I'm going to talk a little bit, this is going to be an introductory session, so I'm going to talk about the need for multi-core microcontrollers, some of the use cases on where we want to use them. I'm also going to give some examples on how we can decompose an application across multiple cores. I think that I found a lot of times that talking to people who are new to multi-core, that kind of can be a struggle for them. So I want to just try to give a couple of examples. Now, our session is, of course, only about 25 minutes. So some of this I'm going to, like I said, it's going to be relatively basic, but I'm going to move through and try to give you some good best practices to walk away from this session with. So with that in mind, let's dive in and start talking about multi-core applications for microcontrollers. Now, if you look back just a couple of years ago, finding a multi-core microcontroller was a pretty rare endeavor. But nowadays it's becoming very common. And I think part of the reason for that is that as we've moved into more and more sophisticated systems, when you look at the IoT, there's been this need, this drive to basically break our problems and systems up into multiple domains. Those multiple domains lend themselves very well to working on individual processors. For example, when we look at IoT, we could have a multi-core processor where one core is just focused on running the Wi-Fi stack and dealing with all that communication with the cloud, while the other core is focused on the real-time embedded system and the main focus of the product. Now, I'm getting a little bit ahead of myself. We're going to talk about use cases here in a little bit, but what I want to get you the idea across is that multi-core applications can solve a lot of challenges, or at least be a tool in our toolbox for solving many challenges. Now, embedded software developers and embedded systems developers are facing a lot of challenges today. Some of these are challenges that really go back to antiquity. Things like quality. How do we develop something that's a good quality? How do we constrain development costs and actually deliver projects on time and in budget? And of course, time to market. These three have been around, like I said, since antiquity. They've been around forever. And I feel like it only sometimes gets worse for us as embedded software developers because we're building more complex systems and yet we're having to do it faster and faster on smaller and smaller budgets. And that really brings the fourth problem or challenge that we face as developers, which is scalable solutions. How do we develop solutions that are scalable and can easily be used to help us improve the quality of our systems, decrease costs, and time to market? Now, as I mentioned, from these ideas here, multi-core processors are one of many tools that we can use, and it can really help us break our system up into different execution environments. Now, one of the things that I kind of see happening in the industry, and this might still be a few years out, but I'm starting to see essentially cores absolutely everywhere. We start out with single cores. We eventually, we're running, back in the day, we were running maybe 4 megahertz as a clock, eventually 8. Then it jumped up to 16 and 48. And now we've got microcontrollers that I've seen running at as much as a gigahertz. So at some point you reach a calculation limit on how much you can do in a single core. And you start to see multiple cores, being used in order to get all the work done. But it's not just that. Some of the advantages of multiple cores is that, yes, I can break up my problem domains or my execution environments, but they can also be used for protecting our device and creating isolation barriers within our applications on basically getting hardware isolation in order to help improve the security of our systems. So while we might see some processors today with 2 cores, and they're probably considered the high-end, high-performance processors by a lot of silicon providers, I think we're going to see in the future, over the next 5-10 years, very simple microcontrollers that are still multi-core become inexpensive and be readily available to us as developers. And because of that, we need to really start to understand how can we use those multiple cores in order to develop our design and develop our applications. Now, there's different types of multi-core processing that we can look at. One is homogeneous multi-core systems. These are systems where basically you have more than one core and both cores share the exact same architecture. So for example, I might have a multi-core processor that has 2 ARM Cortex-M4 processors on it. And then maybe I have one processor I'm going to dedicate to real-time system processing, maybe, and the other one maybe is to updating a display or running a machine learning algorithm or something like that. There's several use cases that we'll take a look at here a little bit later. But the idea is that in homogeneous multi-core systems, we're basically having multi-core systems that have the exact same cores on them, which can simplify, of course, the software model and things like that. Now, there's also, of course, heterogeneous multi-core systems. These essentially have more than one core still, but each core is of a different type of architecture. One of the common architectures that I see out there right now is where you'll have an ARM Cortex-M processor paired with an ARM Cortex-M0 Plus. Now, again, there's lots of different applications for this, but you can look at it as the ARM Cortex-M0 Plus is generally a low power, resource constrained core, whereas a Cortex-M4 is usually a high performance type of core. So you can have a rich execution environment in one core, and maybe when you're not doing things, turn that core off, go into low power mode, and then still have that ARM Cortex-M0 Plus running, which is designed to run at lower energies and be able to conserve battery life, for example. So there's all kinds of different strategies that you can start to pull out of the weeds, essentially, as you move into a multi-core environment. Which is really, to be completely honest, quite exciting. It's a quite exciting time for us embedded software developers. Of course, the complexity is going to, shoot a little bit out of control while we try to figure out how to use these new tools that are available to us. But it's not much different than when the PC industry went from single cores into multi-core, processors as well. So, and even a lot of the techniques can probably be brought over. We just have to make sure that we do so in a way that our systems remain real-time systems and can respond to the events that are occurring in the system in a reasonable period of time that's very deterministic. Okay, so let's talk a little bit right now about the multi-core use cases. There's lots of reasons why we might want to use a multi-core processor, and I've already alluded to a couple of them. Now, one of the first ones, and for these use cases, actually it turns out that ST Microelectronics put together as part of their STM32H7 documentation, they laid out some of these use cases really well. So I am borrowing from their H7 flyers and documentation there, but I think they do a really good job of helping us understand what the core use cases are for us right now as developers. Now, the first use case that I think is really important, that you can see here on this slide, is that we can break our system up into machine learning side, where we have feature-rich environment, and a real-time control side, where we handle all the real-time control. So, one of the use cases for that, as you can see, a lot of people are starting to use machine learning. They're trying to get a good understanding, trying to implement it into their products and their businesses. Whether that fully makes sense or not, or whether it's just hype, we're still kind of in those early stages. Although a lot of really interesting technologies and applications are starting to show themselves. So it's an area that's really important, and a area that I see even some of my clients and customers starting to really start to leverage and take advantage of. But the idea there is you take, maybe if you're using a heterogeneous processor, you have the feature-rich side running the ARM Cortex-M4. You have that do the machine learning, run the inferences. You have the M0 Plus side do motor control, actually do the ADC conversion, sample the sensors, maybe perform real-time communications as well. But the idea here is that we really have two separate problem domains. One is running inferences and machine learning algorithms, and the other is handling real-time control. So we can separate these into two completely different cores, which then, of course, gives us lots of advantages. One, I can break up my development cycle, right? If I have enough engineers, I can say, hey, team 1, your focus is on core 0, and you're doing machine learning algorithms. And team 2, you're going to be doing the real-time control. You're working on the other core, and you're going to be doing all of our real-time control. So you can actually break it up that way. And then even within those teams, if you're using real-time operating system or things like that, you can even further decompose the system even further. So of course, there's got to be overlap because you have to take that real-time data and somehow get it across over into the other core so that something useful can be done with it. But those are kind of the devils in the details, right? How you get those to communicate. And it's going to vary a little bit based on the architecture that you might be working with. Now, the second use case can be where you actually are using, real-time control. So real-time control here, what we might be doing, we may have, again, maybe we're doing PWMs, we're doing some control on motors. We have one core that's, again, just kind of solely focused on that on the one side. And then maybe on the other side, and as part of the ARM Cortex-M7, we still have some type of real-time control. Maybe we're talking to a display unit, we're working with memory. Those are two very highly real-time sensitive applications, right? And so instead of trying to have all that jam-packed and controlled by a single core, we can take all that real-time control and separate out into two different problem domains and let each processor kind of be a master of one of those domains. And anyone who's done any display development and things like that know that it can certainly be challenging, and it can be CPU intensive at times as well. So real-time control, breaking it up into two different pieces is another good way to go as well. Now, a third option here, and again, this is very highly, a very, very good option for IoT, and it holds a special little place in my heart, to be honest, is security solutions. And this is where you essentially have, between the two different cores, you might actually break up and have one core be completely a security processor. So you do all your cryptographic operations and things like that. You do all of that in one core. And then in the other core, you have kind of your application rich area where you don't have any cryptographic calculations. You don't have any keys or any of that stuff. You just have your main application. So this becomes a good way to provide hardware-based isolation between the two cores, which anyone who's involved in security knows isolation is absolutely key. We want hardware-based isolation. We want it in each of those cores then to maybe be able to even boil down further and use MPUs or PPUs and other types of resources that are available to us in order to be able to really secure the system. So this is another example of what you might do. And this is just a couple of things, a couple of example use cases. There's certainly plenty of other ones. A fourth use case that comes immediately to mind is, again, putting all the Wi-Fi code in one core and then all of our actual application code in the other. And the list just goes on and on and on. It really depends what it is that you're trying to do. A fifth use case would be if you're trying to save energy or you have a low power device that's battery operated. Put the minimal housekeeping stuff in your low power core and then only wake up and run the high Cortex-M7 or M4 when you are going to be trying to get something that requires more computing power done. So you can almost think of that as, maybe you're watching for wake words, for example, in the Cortex-M0 Plus, and when you hear something, you wake up, you fire up Wi-Fi, you collect more data, and you shoot it off to the cloud to do some type of processing or something like that. So really the applications, I think, are just nearly endless, but these are, I've selected these top 5 just because this is what I really see happening a lot in industry as I go out and talk to people, as I work with my clients and customers and things like that. So, but there's certainly plenty of other options out there as well. Okay. Now, that's at least a quick overview of some of the things that we can do with multi-core processing. I do want to try to give you guys a little bit more detailed understanding. So what I'm going to do, there's lots of different vendors out there. I happen to be working with an STM32H757 recently. So I pulled some examples from there. We'll take a look at what some of the hardware looks like, and then I'll try to show you a quick example of how we can decompose an application into multiple cores. So, and then that will hopefully give you a couple of ideas of where you can go from here. All right, so taking a look here, one example of a multi-core architecture is the STM32H757. This particular processor has an ARM Cortex-M4 and it has an ARM Cortex-M7 processor. So what you'll find here that's kind of interesting is that we do have two different cores. And what this does for us as embedded software developers is it does provide us with a couple of different software models to develop our products. So if I'm going to be working, for example, maybe I'm a single developer, I'm going to work on both parts. I can still go to the ARM Cortex-M4 handbook and I can, read up on how I develop my code and how to design a system for Cortex-M4. All of that still applies on the M4 side. I can go to the Cortex-M7 side, go through the documentation. I can develop just like I normally would for Cortex-M7. What you are gonna find here is, as you look through this, if you look through the hardware diagram here, you will find that there are areas where you get an overlap between where the Cortex-M7 and the M4 processor can actually communicate together. So for example, here you can see between the 64-bit AXI bus here, there is a 200 megahertz bus that connects as well to the 32-bit AHB bus on the Cortex-M4 here. So you can see here, there's these pass-throughs so that these guys can actually communicate. There's shared memory locations. Sometimes there are shared peripherals. You're going to find that there are actually hardware-based semaphores and things like that so that the two cores can communicate and say, hey, go to this point and stop. Hey, you go to here and stop. So you can coordinate behavior between these two cores. And this is probably perhaps a thing that is, at least for embedded software developers at first, that's one of those things that you just have to kind of get used to, is that idea that you have two separate cores. Two separate cores literally means if I want to debug my system, I have to load code onto the first core, and I also have to load code on the second core. And then generally speaking, you'll find that you just debug one core at a time. So, but you do have to set up your debug script so that you can load code for both. Otherwise, you might not be able to fully test your application. So that there is a level of additional sophistication there and troubleshooting, debugging that can make things a little bit more complicated. But it's kind of that initial curve of, as you learn it, it seems really complicated at first, and then once you suddenly get something working, you're like, oh, this really isn't that bad. I've got this. So I guess what I'm saying is, don't let some of these little complications and things like that discourage you from actually using a multi-core processor. If you have the opportunity to get a dev board early, play with it, start to understand the technology even before you need to use it. That way, when you do need it, you actually have an idea of how things work and what needs to be done. So, and you'll find too that sometimes programming both cores can be completely different depending on the tool chain that you're using. So I'm not going to show any examples of how we do those types of things today. Okay, now another interesting thing to keep in mind here is that even the boot sequence can be completely different for us when we're using a multi-core processor. When we have a single core processor, the thing boots up and it starts executing our code. Not a big deal. When it comes to a multi-core system, we actually have the ability to choose how the two cores are going to boot. For example, I can boot both of these simultaneously, a CM, the Cortex-M4 and M7. Both come up together, and I just let them run. Maybe I don't need to synchronize their behavior in any sort of way. But maybe I have some type of application where I do want to do that. Maybe I have, I'm working on, I've actually separated the use case where I'm looking at security, for example. And what I need to do is I want to boot the CM4 first, have it do some cryptographic stuff, verify applications, yada, yada. And then I want to start the M7. So I can actually control that boot sequence. I can either simultaneously boot them both. I can have the CM4 boot first and then the Cortex-M7, or I can have the M7 boot first and then have it turn on the M4. So lots of different control there. Again, you just got to look at your application, see what makes the most sense for you. But suddenly there's lots of options here as we move into multi-processors on how that boot sequence looks. And each core can boot up kind of in the same way that you would normally find a single core processor to do. So it's not a completely brand new way of thinking for us. It's just there's a new way to start to coordinate behavior and a new level of control on how the application behaves in the hardware. Now, one of the things I mentioned a little bit earlier is that there are most multi-core processors will have some type of hardware-based semaphore. The STM32 parts have this HSEM peripheral, which actually provides 32 semaphores in hardware that basically allow you to make the two different cores synchronize their software if you need to. So what ends up happening here is it's just a simple way to manage access permissions and then synchronize the use of resources between multiple processors. Pretty straightforward and simple. I could probably give an entire 25-minute presentation just on how these things work, but I know we're running a little bit short on time, so I'm going to move along. If you do want, I'll give you some resources here that you can go to after this, where you can learn a little bit more about these things, or at least a little bit more about multi-core processors if you want to. Okay, now this is the part that I've really been looking forward to in the talk, is to talk a little bit to you guys about how to develop a multi-core application. Now, you will find that when you are going to decompose a system, like most of us are using RTOSs, I think, in the IoT space. Maybe if you're using a very low power device, maybe you're just going bare metal. But most, probably 90% of the people I run into are using some type of RTOS-based system. Now, normally what we'll do is we'll go through and identify, there's a step that we follow to decompose an application. We identify our major components. We draw a high-level block diagram. We label our inputs and outputs. We kind of identify what our first-tier tasks are. We determine the concurrency levels and dependencies of these tasks compared to each other. And then we identify kind of high, not high level, but we define second-tier tasks, which are all of our application codes, components. Now, what ends up happening if you go through that process, you will create, you'll decompose a system that might look something like this. This is a simple IoT device. It's got 6 tasks. A core application task. It's got a process inputs task, a network manager task, and then I've got a printing task, a process outputs task, and a memory manager. So kind of a simple, you could consider this thing to be, I guess it's not fully a sensor node, but it's something that's got a little LCD and can control, some things. But in any event, for our purposes, you can see here a very simple flow of data. Data comes in from the sensors. There's a mutex here to share data process between the application, a semaphore to notify the application that something's being done, or that data is available. And then we have some queues to pass data to and from the network. And the application does some processing, and then it controls the output of the system, maybe stores some information, then display something on an LCD. Very quick 30-second overview of what this thing is doing. Now, this is what the application might look like for a single core processor. But let's say we now have a dual core processor. Well, the decomposition process can be very similar, but it can also is going to have some little extra caveats. Because we have this multi-core system here now, we can, first of all, we want to partition our application into application domains. So I want to see, how can I break these into multiple domains and best use my multi-core processor? Once I've figured out how I can partition the application domains, then I can decompose each of those application domains into execution domains, essentially, of what tasks should actually be running on which cores. Once I've done that, I can identify any domain concurrencies and any shared resources that need to be managed between the two cores, between my application domains. And then what I need to do is just synchronize across those different domains, the tasks, because I might have different tasks that need to communicate with each other or, pass data from one to the other. Now, what that can do for us here is what we might find is that can have a pretty big change in our software architecture. You can see here what I've done here now with the original architecture. I got core 0 now over here. I'm calling this a real-time core. And then I've got core 1 over here, which I'm calling high-performance core. And what you can see here is I've kind of broken up the data. These red lines are basically showing, hey, this is where the hardware-based boundary is for the different processors. And then I've created this shared region to try to identify, what is going between these cores. How are they communicating together? And in this particular example, you can see I've actually kind of rearranged things. They're flip-flopped from before. You can see the network manager is on the right-hand side. I've put this in the high-performance core. So all my Wi-Fi, Bluetooth communication, interactions with my application are over here. And then all the real-time tasks, processing inputs, printing to the display, or processing the outputs, this is all now in the other core. And what happens here is data comes in, it's going into the, process data store just like before. So this is some shared RAM, for example. I might be using a hardware-based semaphore to signal that, hey, there's data there. This application can then go over here, consume the semaphore, access the data, do its processing, and then it can come back over here and send the results to the processing output task and also the display using just a memory location. Maybe, again, I might have a semaphore or something like that to see what's going on. It depends on, do I have real-time operating systems running separately in each core? Do I have an RTOS that can manage multiple cores simultaneously? A lot of these details are going to be dependent on what exactly you're using, but from a high-level architectural standpoint, we can say, okay, yeah, this is just nothing more than a memory location where we're going to put data in there, and then it'll be signaled to the other core that something's going on there. So this is one way that I could arrange that architecture. Another way that I could arrange the architecture in order to try to simplify things is that perhaps in the original one here, I collect data, I put it here, the application processes it. With a multi-core processor, maybe that's not fully necessary. If the real-time core can do the processing itself, I can change my application so that I bring in my sensor data. I then have some application core that will process this data. Maybe some of the results are then passed over to the application core, where maybe the application and the network manager here are doing nothing more than, basically managing the network traffic or commands from the cloud or something like that. So you can see the real-time core is basically handling anything to do with inputs, outputs, input processing, and then it's just sharing some data back to the application core, which may be relaying raw data, current status of the real-time system or whatever over Bluetooth or Wi-Fi. And maybe we have new data coming in here that's then processed and pushed through to be able to adjust some of the settings on the system. Lots of different ways that we could architect this, but this is at least giving you an idea of a couple of things that we could potentially do with a multi-core processor. Okay, so with that in mind anyways, this gives you a little bit of an idea about some of the things that you can do with multi-core processors. If you are interested in learning a little bit more about this, I did have a design news presentation that I gave a while back as part of the DigiKey Continuing Education Center on multi-core processors. It's a 5-session, 30 minutes each, goes in a lot more detail. It's free. So if you want to learn a little bit more, you can always check that out. You can get to it from my blog at beningo.com under blog, and then just under Design News CEC categories, and you'll see all the courses and stuff like that I have for free. So I greatly appreciate your time and attention today. Hopefully you took a best practice or two out of the discussion and will consider using multi-core processors in some of your future applications. I know I certainly am, and I'm really excited to see where multi-core microcontrollers go over the next several years. So thanks a lot for attending my talk, and I hope you enjoy the rest of ARM Dev Summit and find some great best practices and tips to take back to the office. Thanks, and if you do have any questions, feel free to email me at jacob@beningo.com.